The next presentation is from Ingrid Haedrich, who is head of group degradation analysis and modeling PV modules at Fraunhofer ISE. And Ingrid is going to talk about the recent reliability aspects from Fraunhofer ISE's testing and calibration laboratory, TOPCon degradation, deviation from nominal power, and glass breakage are the three hot topics she is going to cover in her today's presentation. Ingrid, the floor is yours.
Thank you very much for the kind introduction. I'm gonna quickly share my slides. Welcome to my presentation about basically topics we are working on a lot in our test lab for PV modules at Fraunhofer ISE and in our calibration lab. I divided my talk into three parts. One is UVID of TOPCon. The other one will be glass breakage and our recent results on that. And as a last part, I will shortly talk quickly about the label deviation, but moreover, I'm going to talk about storage effects, which we investigated in our calibration lab lately. So again, who are we? Fraunhofer ISE, we have basically two test labs. One is the Color PV modules, which is a calibrated laboratory. We have a leading measurement uncertainty of 1.1% for PMP. And we are existing for more than 15 years, and that allowed us to trace back our measurement stability for more than 12 years now. The other part is we have a test laboratory. We are accredited according to 17025. We are referring ourselves to the PTB, and we are also the certification body is the VDE. So based from these two laboratories, we are investigating many other things. So we look into, we do a lot of failure analysis. We try to do a lot of root cause analysis for customers. And we try to understand degradation mechanisms in detail. And try to quantify them. So again, today I would like to talk about three topics: the UVID of TOPCon, glass breakage, and metastability effects and storage effects in the lab. So let's start with TOPCon UVID. So it's been almost 2 years now that we published that we saw that strange effect in a normal sequence B. That we measured the modules initially, and then we measured the modules after UV 60 test, and then again after a humidity freeze test, and we discovered that modules behaved very strangely, that there was a degradation and then a recovery. And over the past 2 years, we learned, well, there is a metastability effect caused by dark storage. And meanwhile, I think the world knows that after every UV test, you need to stabilize the module, usually done with a simple light soaking in the lab. That meant for us, we had to change our processes in the test lab. So now it's common that whenever we run a stress test, after that, the modules go immediately into a light soaking, and then we measure STC and EL images. Meanwhile, it's also known that the UVID effect is caused by somewhat hydrogen migration in the cell. So it's a cell intrinsic effect. We've learned already from the talks beforehand how module producers are working on avoiding this effect. For us now, the key question is though, how does a UVID test indoor actually correlate with the effective degradation in the field? Because still after stabilization in the lab, we still see various results. Some modules show almost no UV degradation, others show more. But the question is, what does it mean for outdoor exposure? And so Today, I would like to talk about two effects which we investigated. One is the direct comparison between UV degradation indoors versus on 3 outdoor sites. And the other part, I would like to talk quickly about dark storage effects and how they impact the outdoor behavior. So here we see the results just published on EU PVSec, where we have 3 outdoor test fields where 3 different type of modules were exposed, of which one was a PERC module and the other 2 sites had TOPCon modules installed. And we compared here the results, so taking the module coming out of the field and degrade them in an indoor UV chamber versus for 60 kilowatt hours versus what happens if they stay a year outdoors or correlated to the same UV dosage outdoors. And what we find that there is a consistent trend that we overestimate the UV degradation indoors slightly, not much, but slightly. Curious enough, we also observed it with a PERC module where we wouldn't have expected such a high UV degradation. But surely for TOPCon, the result was that we see more UV degradation if we test indoors. Possible reasons for this overestimation could be that we don't reach the 5% of total in-plane irradiance. It is not always 100% clear what irradiance we had outdoors in the field because we didn't measure the UV dosage outdoors exactly. We just took it from weather data. We do know quite exactly what our UV spectrum is in the lab, but also it's not yet fully clear which part of the UV spectrum is more prone to cause a degradation. Also, we could not consider any temperature effect. In general, it's still a good result in terms of that we get a better feeling for how close we are with our indoor testing. And maybe it raises the question whether we have to change slightly the indoor testing or we should have a different correlation and we keep on working on this topic. The other part was we do know that modules have a dark storage effect. So if they are in a condition in absence of light, the power decreases until the module sees light again. So here we did a little test. We took modules which were installed in the field for about a year already, and then we just turned them upside down in the field, and then for about 4 or 5 hours, and then we turned them around. Then we measured them, and then we turned them around, gave them a little bit of light soaking in the field and measured them again. So what we saw here, and it's probably not surprising, also in the field, after a year of installation, we can see a dark storage effect of about 0.6% degradation over a duration of 4 hours. And then we also see that the light stabilization just by holding it into the sun in the field happens very, very quickly. So the next question we wanted to answer was, does that change something in the behavior, let's say in the morning? So the sun rises, and do we see a difference in modules which are new, so which haven't seen any UV degradation versus modules which are pre-age, so which been into a UV chamber? And the answer is no. So we don't think that the degradation or UV degradation or dark storage effect has a major influence in the behavior or in the energy yield or power output over a daily curve. What is though to consider, or what needs to be considered, is that when we have drones flying over the PV field or PV installation during the night, then the dark storage time is long enough that the modules might have degraded by 1%. And this is what you see then in EL images taken by drones in the night. And we do have more and more customers being concerned. They see dark cells in the night in the EL images, and they wonder what it is. And basically our answer is, well, it's probably a UVID effect of TopCon, which is recoverable, but you will only find that out if you run an EL images after giving or directly after the modules were exposed to light. The next topic I'd like to talk about is the whole class breakage, which is also still a topic in nowadays field failures. And here again, we started working or looking into it about 2 years ago. We know that it's connected, that the class breakage is connected, that there are that the module area is bigger, that the module design has changed to very, very low thicknesses of glass, 2 millimeter and less. In previous publications, we showed already that there is a correlation between the glass thickness, the pre-stress of the glass, and the failure loads they can cause. But also we've learned it's not as direct. So it's not, you cannot say that a glass which is 1.6 millimeter thick has generally a lower stability than a module which uses 2 millimeter glass. But also we've learned that comparing indoor and outdoor testing again, so looking at glass patterns from the field, we see these large round-shaped breakages, whereas when we test according to IEC 61215, the mechanical load test, we usually see fracture patterns which are much more confused and much more fine. So we looked more into that topic, or maybe I should say, so that means whatever IEC 61215 is testing at the moment, it's not efficient or not suitable for what actually happens in the field. So we know we have to invent or adapt our tests, and whatever the IEC norm is telling us to test is still necessary, but it doesn't help to predict whether this module will show glass breakage in the field. So here again, these are the typical patterns we see in the field, or which are brought to us from field modules. Again, very singular cracks, very round shaped. So whereas in the lab we have a very chaotic crack pattern. Furthermore, we know that in the lab we apply very high surface loads. So we press with 2,400 Pascal on a module, whereas we know from simulations where we applied inhomogeneous loads, which you can also find in other publications, that we get closer to the fracture pattern we see in the field if we apply just low loads. Furthermore, in the lab, we see the crack origins usually appearing at the edge or where the clamps are, whereas in the field we see that the cracks start likely at surface defect somewhere in the middle of the module. Furthermore, the fracture pattern we see in the field is known in science or from literature, and it's contributed to in literature for surface pressure fractures in laminated glass with heat strengthened glass. And furthermore, the literature says that it could be an indication for undersized glazing. Furthermore, we observed another effect in the field. We call it the sagging of laminates. between the frames. So when we look in the field at modules which are installed, since they are very large, they are constantly hanging between the frame. And it's also known that this causes somewhat of a pre-stress of a glass as well. If it keeps on sagging like that for a long time in the field, that the glass is constantly under stress, which then makes it more likely to cause breakage patterns. We did simulate that with finite element investigations. And if we do so, we see that the lines here of how the glass is under stress from just hanging is very much the lines we see in the field later on when the glass starts to break. So another question we are often asked is how can we, or what can be done maybe in a module production in a non-destructive method to inspect the glass and to get more information about glass quality. And so some ideas would be that you measure the pre-stress of the glass with a polariscope. There are some transillumination methods where you can check the homogeneity of the pre-stress of the glass with basically with a polarized light looking through the glass. You could maybe do some microscopic scanning along the glass edge, which is also can also cause quickly glass breakage. Or maybe there is an option to have an eye-based visual inspection for detection of glass inclusions. But it's still, we think, will this be sufficient? And a general question we are often asked is, should we harden the module to survive the environment, or should the environment adapt to the module, meaning maybe have a better mowing system or just try to avoid stones hitting the glass? Or is the answer both should be done? What we've learned from the module manufacturers already, that they do work effectively and hardly on trying to improve the glass quality. And so I think this is one way of going, but maybe we can do also work on other sides. So the last topic I'd like to talk about is the metastability and storage effects. So again, here I would like to specifically talk about TopCon, but now we are not looking into UV-ID. So the module has seen any UV lights, or rather we look at modules which are out of the box. And then we look how stable they are. But first, I would like to share some slides from my last year's presentations where we looked at the label deviation between what we measure in our calibration lab versus what we see printed on the label. And I think the chart is very well known, but now updated for last year's results. So we did see over a duration from 2012 to now 2024 that the deviation between what we measure versus the label increased strongly to a negative part, up to 1.3% average deviation in 2023. The good news is our last data set in 2024 now shows that there is an improvement. So instead by 0.2%. So we only have measured last year a deviation between label and our measurements of 1.1%. So it seems that there might be a change in the trend regarding this topic. So again, the other topic is storage and light soaking of out of the box modules. So we did a little test. We measured the module coming to the lab. Then we just placed the modules for several months in our lab under normal lab conditions. So there's always a bit of light on. It's never fully dark, or maybe in the night we switch off the light and then it becomes darker. And we did that in two sequentially. And in between, we also we did light soaking to see how big the dark storage effect would be. So here are the results. So we measured the module in total for 16 months. And we measured 2 different types of TopCon modules. And what we see is that the degradation rate in average from these 2 modules would be 0.1% per month. We see that the light soaking immediately recovers the effect, but over a longer time, the dark storage effect can cause up to 0.6% decrease in power. This is especially concerning us for our reference golden modules. So meaning a module producer sends us modules from their production line and it's shipped through the world, then into our lab. Then we do the light soaking, we measure it, and then we ship them back to the module producer so that they can use it as to adjust their line flasher. And here, I think this result shows clearly that when the module goes back to the module producer, the modules need to be light soaked or stored in somewhat way that they are under somewhat light. Otherwise, the deviation would, if they would be stored in a dark way, or only in the dark, then the degradation would increase, and that would cause significantly deviations in the measurements, in the measurement accuracy in the module line. With that, I'd like to thank you for your attention.
Thanks a lot, Ingrid. Indeed, each topic what you dealt today in this presentation should be a separate topic. I know how difficult was for you to compress everything in such a short presentation, but I think that's really great. One quick question. So you mentioned undersized glazing as part of the glass-based degradation. So does it mean is the lower thickness than the recommended?
No, I wouldn't say that. So I think probably the safest way would always go to really thick glass of 3 millimeter, because then you have a full tempering process. And we know that this glass is more stable. But to go directly and say 1.6 millimeter glass is much, much worse than 2 millimeter glass, that's not what our results showed. It's the tempering, like we see, they have all a lower pre-stress, but not completely low, or there is still a pre-stress there. The question is it enough to protect, to withstand when a stone hits the glass, or what would be the right pre-stress level that a stone can hit the glass and nothing would happen and the glass wouldn't break? And that's our ongoing research at the moment.
Okay, great. Thanks a lot. I think there are also a few questions in the chat window. So till again we meet in the panel, please enjoy our conference and try to answer these questions in the chat.